Welcome to the topic deflection of beams, problems and solutions. Deflection of pre-stressed concrete beams concept already explained, but here before going to problems and solutions, it is better to recall all the formulas once again. I will go one by one. A simply supported beam carrying a central concentrated load. The formula is WL cube divided by 48A. A simply supported beam carrying UDL 5WL raised to 4 divided by 384A. And pre-stressing force will create a deflection. And there are different cable profiles. I will discuss. First one is a triangular shaped cable. Here this cable is having an eccentricity at the ends. If the eccentricity is there at the ends, there is a end moment, that is M equal to P into that eccentricity, that is eccentricity at the ends is E2. Because of this triangular shape of the cable, there is a creation of upward point load, that is 2p tan theta. Tan theta is opposite by adjacent, which is opposite. Suppose this is theta. If you draw, this is the triangle. In this triangle, opposite is E1 plus E2, and this is adjacent is L by 2, E1 plus E2 by L by 2. That is a point load. That is just due to the cable profile, triangular cable profile. This case will create two deflection, that is one due to M, another due to this point load. This will create a downward deflection and this will create a upward deflection. Total deflection due to that pre-stressing force is ML square by 80A minus WC into L cube divided by 48A. If this E2 is 0, that means eccentricity at the ends is 0, this moment will vanish. Then only this WC exists. Then only one eccentricity is there, that is E1, that can be taken as E. Then tan theta will be simply E divided by L by 2. E divided by L by 2. Because of there is no M, only WC is there. The formula is WC L cube divided by 48A. The negative sign is this will create a upward deflection. Next, this is another cable profile. This is a parabolic or curved profile. Here eccentricity at the ends is E2. Once eccentricity is there at ends, then again moment is there, as in the last case. And because of this cable profile, instead of this point load creation, WC created in the previous case was a point load because of triangular shape. Because of this curved shape, there is a creation of a UDL, that is 8PE by L square. 8PE by L square. This E is total eccentricity E1 plus E2. Here two forces are responsible for deflection. This is moment and this is one will create a downward deflection, another is upward deflection. That's why ML square by 80A minus UDL formula is 5WL raised to 4 divided by 384A. As in the previous case, suppose if you make at the end C2 is 0, M will vanish, only E1 exists, can be taken as E. WC is simply 8PE by L square. M is not there, therefore only one deflection, that is due to upward UDL 5WL raised to 4 divided by 384A. Then due to dead load, How to calculate deflection? This is again UDL. Formula is simply 5WL raised to 4 divided by 384A. That formula is known. I'm not mentioning again the formula, but how to calculate dead weight, that is volume into density. Volume is B into D into 1 into density of concrete. Here 1 is in meter, density is in kilonewton per meter cube, hence B and D should be in meters. Suppose E is not given, Young's modulus is not given, FCK must be given. By using FCK, how to calculate Young's modulus? You know the formula, 5700 root FCK. How to calculate moment of inertia? You know, BD cube by 12. And sometimes section dimensions are not given, B and D are not given. In that case, cross-sectional area is given and radius of gyration is given. You know the formula for radius of gyration. Radius of gyration K is equal to the formula is root of I by A. You know from engineering mechanics. If you simplify this formula, I will become K into A square. Then come to how to calculate short-term deflection, that is delta due to pre-stressing force, delta due to dead load and delta due to live load. If the deflection at transfer is given in the problem, you calculate only due to P and dead load. If simply short-term deflection is asked, you calculate for all the case, combination of P, dead load and live load. Long-term deflection is considered by considering the loss of pre-stress and creep coefficient. This is Lin's formula, you know already. Delta of dead load and live load minus delta of pre-stressing force and PF by PA. This is called as loss ratio into 1 plus 5. This is Lin's ratio. Remember it. Then come to problem. This is the first problem. These are the VTU problems. Some 3 problems are solved here. You come to the first problem. Here given data is 150 mm, that is cross-section dimension. 150 mm is B. Overall depth is 300 mm. The span given is 8 meter. And eccentricity at the center is 80 mm, that is E1. And eccentricity at the ends is 30 mm. And the pre-stressing force is given, that is 350 kilonewton. Sometimes P may not be given directly. In that case, there should be a pre-stress, that is in Newton per mm square. It is above or around 1000 Newton per mm square. And cables are given, number of cables and diameter of the cables are given. That is AS into FS, you will get P. Here P is directly given, there is no problem. And what are the external loads given? External loads are live loads given are 10 kilonewton central concentrated load, and live load is also given WQ. Q is actually external UDL I have mentioned. That is 2 kilonewton per meter. Here required data is short-term deflection due to pre-stress and self-height. It is clearly mentioned, pre-stress and self-height. Don't go for adding live load deflection. Short-term deflection due to pre-stress and self-height will restrict to only that much. Then long-term deflection due to pre-stress, and there is a loss of pre-stress 20% and creep coefficient 1.8. And check the deflection as per IS 1343/1980. And let us see the first case, short-term deflection due to pre-stress and self-height. Here, this is the free body diagram with all loadings. Here at the ends M is there because at the ends there is eccentricity. What is M? It is calculated somewhere here. P into E. E is in mm. It is converted to meter divided by 1000. That is M is 10.50 kilonewton meter. And self-height is calculated by multiplying B into D, and 1 meter length is there. It is not written. 25 the density. 1.125 kilonewton per meter is the self-weight, that is UDL, that is acting downward. And due to cable profile, there is upward UDL, WC. WC is calculated by using the formula 8PE by L square. This E means combination of E1 plus E2, that is 80 plus 30, that is 110. That upward UDL is 4.8125 kilonewton per meter. Here, self-weight is UDL and this WC is also UDL, downward and upward. I don't combine this UDL because I want a deflection of beam due to dead load separately and deflection due to pre-stress is separate. Deflection due to pre-stress is due to M and WC. Deflection due to dead weight I want separately. That's why I don't combine these two UDLs. I will take it separately. Now come to deflection, short-term deflection due to P and dead load. Due to self-weight, 5W L raised to 4 divided by 384A. This is a positive value because dead weight is acting downward deflection it will create, that is 4.931934 downward deflection, that is mm. Then due to WC, it is upward UDL. Here the formula is same for this also, 5WC L raised to 4 to 384A. Here only difference is 5 is same, L raised to 4, 384, both all are same, only UDL is changed. For W's of 1.125, this is the deflection created. For 4.8125, how much? You can use this formula to calculate deflection due to WC, or you can go with the formula, this one. This takes time unnecessarily, that's why you can use this one. Then deflection due to WC is 21.10. It is upward. It is actually minus. I have not written. While combining, you can put minus. Deflection due to M, direct formula ML square by 8A, that is 6.904 mm, that is downward. Now short-term deflection due to P and dead load, I will combine now. 4.934 is due to dead load, is downward positive. This is due to WC, upward deflection minus. This is due to M. On combination, final deflection will be 9.262, the negative value, that is upward deflection. Deflection due to P and dead load should be always a negative one. You cannot get positive. If you get a positive, it is simply a foolishness of developing a downward deflection at the transfer. Nobody will develop a downward deflection at the transfer. It should be upward deflection, because why upward deflection is to balance the downward deflection due to external loads. That's why it is always minus. If you get a positive value, you should be very careful. You should check it once again. Then come to long-term deflection, considering loss is 20%. Use Lin's formula. Now we want deflection due to live load. Dead load is already in there. We can use that one. Due to live load, how much is the deflection? Let us calculate first. Delta due to live load is due to point load WL cube divided by 48A, that is downward, that's a positive. Then external UDL, that is 2 kilonewton per meter. Again, you can use this formula or this one, simplified one. That is for 1.125, 4.934. For 2 is how much? You can directly calculate. This is the total deflection due to external loads. One is due to point load, another is due to UDL. Total is 17.54. And here PF by PI, that is 0.8. Because loss is 20%, that loss ratio is 0.8. Use Lin's formula. After using Lin's formula, What is deflection due to dead load and live load? Due to dead load 4.934. Due to live load, both are downward deflection. Total is 22.474. That is mentioned here. Minus. Then due to pre-stress, only due to pre-stress. That is, this is due to WC. This is due to M. Then the total will be minus 14 point. This minus already is there here. Minus. Don't use again minus. It will become plus. That's why it is minus only. This no need to use minus once again here. This minus is there already. This minus is there. That's why directly you take this 14.196. Then after simplification, long-term deflection is 31.13 mm. As per IS 1343/1980, the deflection should be restricted to span divided by 250, that is 8000 divided by 232 mm. Deflection developed is well within the limit. Even though if it is more, developed is more, you cannot do anything because it is not the design problem. We are simply checking the deflection. How much deflection developed? Is it within the limit or not? You just comment on this. This is within the limit, it is okay. Then come to second problem. Here, a similar problem. But as I said already, here cross-section dimensions are not given. Here directly area is given. And radius of gyration is given. And loss is neglected. There is no loss. And eccentricity at the ends is not given, that is 0. Only eccentricity at the midspan is given. Here pre-stressing force is not given, as I said already. Area of steel is given, 6 number of cables, each cable diameter is 7 mm. And definitely Fs is given. Pre-stress 1000 Newton per mm square. Young's modulus is given directly, that is 38 kilonewton per mm square. Here required data is central deflection due to self-weight and pre-stress, and due to self-weight, pre-stress and live load of 2 kilonewton per meter. Then come to first case. Self-weight plus pre-stress. Here self-weight you can calculate. Self-weight is B into D into 1 into density, but here B and D are not given. Instead of B and D, area is directly given, therefore you can calculate. Area is given in mm square, that should be converted to meter square divided by 1000 square. 24 it is given, don't take 25, density of concrete is given. Therefore dead weight is 0.768 kilonewton per meter. That is here. Due to cable profile, WC will be created. WC, that is 8 PE by L square. Here 8 PE by L square. 8 P is calculated here. See, P is equal to FSAS, that is, you will get in Newton, that should be converted to kilonewton, this much of P. And I is also calculated separately, that is, we know the formula. Radius of gyration is square root of I by A. K square is IA, then I is equal to K square into A. In the previous discussion during that discussion in the note, it is mentioned as a square, but a square is not right. K square a is right. After simplification of this, if you squaring both sides, it is k square. It is not k into a square. Remember, change it. Okay, self-height is acting downward, WC is acting upward. There is no moment at the ends. M is not there. Only self-height will create, and this will create deflection. Here, there is no loss and also creep coefficient. That's why, because of that, I am going to combine both. Otherwise, you can calculate separately also. Self-height and pre-stressing force separately. Pre-stressing force means WC, and this is WG, dead weight. You can calculate dead weight deflection separately and WC separately and then combine. Otherwise, you can combine these two, because in the long-term deflection, or here long-term deflection is not there. That's why I'm going to combine. This is downward and this is upward. Upward is more. Upward is WC is 1.433. Downward is 0.768. If you calculate the net UDL, this is this minus this, you will get 0.675 Newton per mm or kilonewton per meter. That means I converted 2 UDL as a single UDL. If there is a long-term deflection is going to calculate, means you calculate dead weight deflection separately and WC separately. Okay. Now converted 2 UDLs as a single UDL. Now upward deflection is there, that is because of this one, 5W L raised to 4 divided by 384A. Here net UDL is 0.675, then 5.71 mm. Instead of writing minus, I wrote a sign, that is upward sign. Then come to deflection due to self-height, pre-stress and external load 2 kilonewton per meter. Already we know this value due to self-height and pre-stress, that is minus 5.71. Then this is definitely a downward, minus 5.71 for this one. This is live load deflection, that is 5W L raised to 4 divided by 384 A. Otherwise you can calculate this one in a simple way. For 0.675 this much, for 2 is how much you can calculate, that is a simple way as I discussed earlier. Then the deflection due to P dead load and live load will be 11.21 mm, that is downward. This is well within the limit. L by 250 is 32 mm, developed is only 11.21 mm. Then come to third problem. Here triangular cable is given, and here end eccentricity is given, that is E2 40 mm, and at the center deflection, at center eccentricity, that is 100 mm. Total span of the beam is 3 plus 3 6 meters, and pre-stressing force is given 300 kilonewton. The loss ratio is given. It is not pre-stress loss, it is loss ratio, means PF by PA directly given, that is 0.8. Usually pre-stress loss is given in terms of percentage. At that time PF by PA you have to calculate. Here loss ratio is directly given, that is 0.8. Okay, live load is given 8 kilonewton per meter. FCK is given, that means M40 grade of concrete is given, that means FCK is 40 Newton per mm square. That means Young's modulus should be calculated by using this one. Pre-stress is directly given, there is no problem. Here M will be there, and again point load is created, WC. Pre-stress will create 2 deflections. One is M, another one is due to WC. And due to dead weight, again deflection is there. And due to live load of 8 kN per meter, there is a deflection. Here what is the required data? Let us see. Maximum deflection at transfer of pre-stress, that is due to P and dead load. Now I will calculate separately because loss is given. Due to pre-stress, I will calculate M and WC what it will create, and due to dead load what is the value. I am not going to discuss again and again. Already you know how to calculate M, how to calculate WC, how to calculate dead load. Then here this is the FBD of pre-stress, that is M and WC, and dead load is calculated. Dead load is calculated separately. Dead load is D into D into 1, that is separately calculated. This is due to pre-stressing force, only due to P and WC. Due to P and WC, the formula is ml square by 80A minus WC into L cube divided by 48A. Due to pre-stress, delta will be minus 7.49. This dead weight will create a downward deflection, that is 5WL raised to 4 divided by 384A, that is 1.56. Net deflection due to P and dead load. P created minus 7.49. This dead load created 1.56. The net deflection due to P and dead load will be minus 5.93. Then come to maximum deflection at working load. That means at live load. At live load, loss is given. Once loss is given, it definitely a long-term deflection. Okay, long-term deflection should be calculated. Here phi is not given. Phi is not given means creep is neglected. Again you use Lin's formula. No need to use this multiplication of 1 plus phi because phi is 0. The remaining will be 1 only. Delta due to dead load plus live load minus delta P of PF by PI. Then dead load 1.56 is there, and live load is calculated here. For in the dead load calculation for 0.9 kilonewton per meter, this is the deflection. For 8 kilonewton per meter of live load, how much? That is 8 divided by 0.9 into 1.5. For 1.9, this is the deflection. For 8, it is how much? Otherwise, you can use this formula. There is no issue, but it takes time. Okay, this is due to live load. Dead load is there. And dead load deflection and live load deflection you add. Then this is separately is there. That is minus 7.49 due to M and WC. After substituting all in this equation, you will get a deflection due to pre-stress, dead load and live load will be 9.44 mm, and maximum deflection allowed is 24 mm. That is well within the limit. Thank you.